The main brain of today's AI systems, which rivals human intelligence and makes you fear that ChatGPT 4 will replace you in your dream career one day, or maybe ChatGPT 5 or something like later on versions, is called the transformer architecture. Despite its capacities, this architecture is already archaic, so old and ancient and not really that special, since it has newer versions such as the vision transformer and the sparse transformer, which are both parts of the GPT-4. But nonetheless, it's a very special innovation that we will look at now. Because after all, it set off the AI race. It's all this it's still an innovation. It's still very significant, even if there's like a vision transformer that allows GPTs to create images and process images. Even if there's a sparse transformer, which is like a better version of the regular transformer, the transformer still is a very progressive innovation. But first of all, what I noticed last episode that I didn't do is actually cover some fundamental concepts like special tokens, and in terms of tokenization, like special tokens, the context window, and the special tokens and the context window. So this is something that we'll have to cover now. So essentially, I will break this little notepad into 3 sections. So first we got episode 2. Then we got inputs layer. And then we got transformer architecture. Transformer architecture is probably going to be the biggest one. So I'll make some more space for it, but you don't know fully, so we'll see that later. So episode 2. Let's look at episode 2. What did I miss? First of all, there are special tokens. I'll just make this smaller. Special tokens are very important because they essentially they play a functional role in the model. So essentially, you know of regular tokens, you know that the token 63 could be hello. You know that the token 9700 could be, I don't know, mix, the word mix, right? Anything. It's just very different and dynamic. And but I haven't told you about special tokens. Essentially, if you create like a JSON file, a token vocabulary, right, the .json file, the very first things that come are actually special tokens. So like the 0th token is going to be a special token, the first, the second, and there are 5 main tokens right over here. I think I've said it here. 5 main forms, like tokens that are used. In GPTs there exist 5 main forms of special tokens. So let's break these down. Slowly and surely. So first we got the start of sequence token, start of sequence, and then secondly we have the end of prompt token, end of prompt. Then we have end of reply, Then we have padding and unknown. Now, surprisingly, the start of sequence token is actually not that much in use. It's not actually used that often. Instead, we use these two. So essentially, let me break this down. If you have a sequence, you would expect the start of sequence token, SOS token, to be here, and then end of prompt token over here, EOP, right? Just kind of looking like that. But it's actually not the case. Usually we don't really have SOS. At least ChatGPT 4, for example, does not have SOS. It doesn't really use that. Instead, so essentially these tokens, these 3, are used to differentiate between what the user said and what the GPT said. So like if there's a string of text, like if you're chatting with ChatGPT, you write something, then ChatGPT writes something, then you write something. It's not that it will just look at this big blob of text and try to figure out who wrote what, but instead it will actually have these end of prompt is for every time you write something, like ChatGPT adds an end of prompt thing, then there's an end of reply for its own thing, and then you write something, and then there's an automatic end of prompt addition and automatic end of reply addition. Or even it's like ChatGPT generates one itself, so that it can tell like the system, hey, stop generating more tokens. All right, so that's what happens. So that's start of sequence is not really used. Only this is kind of used, and like just kind of EOR and EOP just kind of tell the model immediately what is going on. Then we have padding tokens. What are padding tokens? Essentially, if you can imagine, let me just cross that out, right? If you can imagine Let me just do that, bullet point all of these. Boom. If you can imagine, if like yeah, you'll have to understand this a bit later. You'll see how this works later. It's a filler token. It's an empty space token, essentially. Usually it's given like the number 0 because that's way easier to understand. It's just like a bunch of zeros. And you can't really generate this, I believe. No, you can actually. You can. We'll break this down. But essentially, you need to understand something called the context window to understand this entirely. Which I'll display here. And the unknown token, essentially, if the dataset of ChatGPT was entirely English, right? I'll just illustrate through this. Was entirely English, Eng dataset. I'll probably have to write it clearer because these notes are going to be in this file later on. And by the way, this file is in the link in the description if you want to see it. And ChatGPT, all right? So English dataset, Eng data. Eng data. So you have this over here. Then if it sees a Russian token, so if you say привет, right? Something like привет, then it will just label it as unknown. Like unknown token, what the hell is this? I don't even know what the hell that is. I don't know. I don't speak Russian, so unknown. Or anything that is just like a special symbol or something like that. If you give it like, I don't know what special, like a Chinese letter. I don't know what Chinese letters look like. I'll just give that looks more Indian anyway. But anyway, it will just, anything that it does not know about, it will just say unknown. All right. And in ChatGPT, there is a specific, so like for if a person is creating their own model, they can choose how exactly it looks like. And for ChatGPT, this is how it looks like. Essentially, if you want, you can go right now and look at this. Try writing end of prompt in this specific syntax. I think I've already mentioned this in previous episodes. Yeah, I think I have. But yeah, it's pretty cool how you can just enter this and essentially ChatGPT will be like, hello, how can I assist you today? And it's just kind of like, it ignored what you said because it doesn't really see it. And if you write that again, it's going to be like, it seems like your message got cut off. I don't understand. Like, what are you trying to do? Can I help you? And something like that. And that's pretty cool. It follows that exact syntax where there's this little bar over here, there's that angle bracket and end of prompt with no spaces in between. So that's pretty cool. And so let me just draw the Russian word over here so that you guys know later on for the notes. So that you know later on for the notes. Anyway, now we've covered all these tokens. Now you have to understand something called the context window. So if I just draw a little thing right here, context window, let me just put something on. So the context window, essentially how it functions is every model has to have a fixed amount of tokens it can accept as input. And I don't know if I've mentioned this in previous episodes, but ChatGPT has a context window of 4096. Its older brother, GPT-4, has a context window of 32K tokens. Essentially, it can accept 32K tokens and that's it, right? So if you can imagine what the text was, I think I've mentioned this in the very first episode, but I'll just reiterate it. You have this, right? You have this entire, let's say it's 100K tokens, right? You've been talking with ChatGPT nonstop. You really want to get something out of it. I don't know. You're interrogating it basically. And let's say you're using GPT-4, it will remember 32K tokens only, the last 32K tokens, which is still a lot. You still, it's like almost 30,000 words. It's like 25,000 words or something like that, 30,000 words approximately, right? You can't actually estimate it correctly. But yeah, it's still a huge number of words and tokens and etc. And it has that in its context window. ChatGPT 3.5, I believe, can only remember 4096 or even 2048. They choose like these numbers that follow this sequence. So 2x. If you put 2 to the power of 16, I believe, you'll get this. I'm not completely sure though. Or maybe it's 2 to the power of 12, I'm not sure, right? Either way, it for some reason follows this sequence. You don't actually have to do that. You can just go with like 500 or something, like a proper number like that. It doesn't actually have to follow that sequence. It can just be like 500 or something, but that's very little. It can be like 4,000 or 32,000 exactly on the dot. but it can be like for GPT-4, I believe it's like that. But anyway, you get the point, right? So let me just draw that over there. 32K tokens. So the context window must stay fixed, and that's because of the neural network. It's because in the neural network, essentially, essentially it's accepting 32K tokens. It's used to computing stuff for 32K tokens. It's used to computing math for 32K tokens, used to working with probability distributions of 32K values. And when you shorten it down or make it larger, it's going to be like, what the hell is going on? Now, probably I'll have to make this smaller for you to understand better. 4096, right? It has to understand what the hell is actually going on. Okay, so this is a very bad representation of a neural network, but you know, either way, you get the point, right? Boom, boom. Then there we go. Yeah, all connections. So that's how it would look like, and it has to be fixed, because if it's less, then it's like I'm not used to that kind of math, if you understand, of the math going on there. So like the weights and biases are adapted to a different type of thing. Maybe I should make this even smaller. Weights and biases are adapted to different types of things. Weights, biases. 4096, I'll just label it like that so that you know. And yeah, so that's what I wanted to cover. Essentially, yeah, what do padding tokens do? So essentially, if you give in, like, you obviously, when you only start the conversation with ChatGPT, you write very little, like a very small sequence. It's obviously not up to the entire context window, and let's imagine that this is the context window. Then it fills this up with zeros, or like with padding tokens. Well, in like a GPT's case, it would be very easy to say 0, but you know, different GPTs vary. So like just essentially padding tokens. And in the ChatGPT model, I believe it was like this, pad, or it was padding, right? I'm not sure, but it's filled with these padding tokens up until it reaches 4096, just for convenience, so that the model can actually work with all of them combined. And so if we look at this, right, that's what padding tokens do essentially. And if your sequence is longer than the context window, which is very rare if you're actually working with an advanced model, then it will just cut that. It will just forget about whatever you wrote, or like more like this, right? Like when you started talking, it will just forget about that, and it will remember the last 4096 tokens, like that. And so yeah, that's how it works. Now we can move on to the inputs layer. I'll just draw that like that. So the inputs layer, how does it function? The inputs layer, now we can drop down over here, and yeah, by the way, if you want to look at that quickly, you can pause it just to look at that. Now the inputs layer does the following. It tokenizes the sequence. So let's just slowly break this down. It tokenizes the sequence. One, tokenize sec. Probably write it like that. Yeah, tokenize sequence. Sometimes this step is done outside of the model. So you could imagine the inputs layer is the part of the neural network. So if you have boom, 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 like that, like a neural network like that, I probably don't have to, I'll draw it anyway, it's kind of satisfying to draw, like that. Okay, yeah, so there we go. This would be the inputs layer. It's part of the neural network, but sometimes you can have it outside, or not, yeah, just outside of the model, and it's like tokenize sequence. It's over here, right? So there, essentially, you take the tokenizer and make it transform every word, every hello or whatever, into a number like 63 or something like that. So first of all, it tokenizes the sequence. Sometimes it can be inside, sometimes it can be outside. Either way, whatever way you do it, like usually it's tokenized inside, but you can do it outside as well. Then, what do we do then? We have adjusting the input sequence, obviously over here, right? Adjust, yeah, just over here. Adjust input sequence. There we go. And essentially, yeah, it does this over here. If we take a look at this over here. and there, over there. Adjust the input sequence so that it's correctly to the size, either with padding tokens or with cutting it up to the correct size. And if it's the correct size, that's completely fine. But it's very unlikely that you will actually generate a proper 4096 tokens equally. But yeah, most of the time it's actually just padded up with padding tokens. But anyway, token embedding. Now this is where it gets a little bit more complicated. You have never heard of this before. This is foreign territory. It has no relation to what is it, episode 2, or it does, but it's not really like direct. You don't really know about this. So token embedding, what it does essentially is give the model more understanding of the words. So essentially now, as you can see here, we replace the tokens that we worked so hard to get in the first place. So here, what we do is, there we go. So essentially, you can imagine you have like, if it's like an array, right? It would be these tokens like 63, 456, right? You give it like into the ChatGPT model, and it tokenizes your stuff up till 4096 tokens in total. Well, we replace the actual token, each actual token, with an array. So now it looks like this. Like this. And what is this array? This array contains small little values of that explain the model, what is going on inside, like what is the token about actually. So essentially, the model can't understand much by looking at this. It can't really understand that this is hello, that this is a greeting, that this is all this. So we need these small little like values that speak in model language, speak in computer language, for the model to understand what the word actually is. And most commonly, how many little values there are is actually 768. Right, that's a number that you'll see commonly, but it's not actually fixed. You know, some different models may, like, I think GPT-4 had like multiple thousand or something like that. I'm not completely sure, but either way, the token embedding was very dense, or like essentially a lot of them, and this is done so that the model can understand what the hell is going on. So if we look here, this is, by the way, this is part of a calculation with weights and biases. There are weights and biases involved. So, and I think I've broken down weights and biases in section 1. I think, I'm not completely, or not section 1, episode 1, I'm not completely sure. But weights and biases are essentially, they are adjusted over time. If you can imagine a neural network over here, they are adjusted over time. Each neuron has them, and they're initially random, but over time, as you train the model, they become more and more accurate and specific to the task that the model is trying to accomplish. And so here, if you could imagine, like at the inputs layer, there are the embedding function over here, the embedding going on over here. These neurons have the weights and biases, and over time, these weights and biases, over training stages, over backpropagation, optimization, all this stuff that will be covered in later episodes, they become more accurate in telling the model about the word. So yeah, it's like little computer. So if you could imagine, we have a token that is like 63, right? It is hello. I don't know why I universally accepted that 63 is hello, but yeah, so yeah, hello. We have the greeting over there. Then but the model doesn't understand this, so we give it a bunch of token embeddings, and all of these little values of 768 values tell it like it's a greeting, right? That it is let me just write that there. Greeting, start of conversation, start of convo, so on, right? And it tells the model way more, and this is, by the way, in model language. It's not actually in tokens represented, these token embeddings, but like very small values, sometimes negative, sometimes positive, etc. And the math that happens there to generate this over the entire 63 is actually very, like, it's pretty much out the scope of this episode. It's kind of difficult to explain, but just know that there's math that goes on to actually do that. Then, fourth one, and this is, okay, we're jumping ahead a little bit here, but let me just... There we go. Positional encoding. So what is this? All right, pause, enc. And I have to define a boundary over here so that I have space for the transformer architecture. I don't have much space here, but that's fine. I'll just probably do this. Okay, that's a very odd shape, but anyway. Positional encodings, why do they occur? So essentially we have now what would look like, imagine if we have a shape, right? Hopefully you can understand how this looks like. A shape of 496 embedding vectors, each of which have 768 embeddings. And that's how the shape looks like. And by the way, if you're not really familiar with shapes, 1, 2, this shape 1, 2 would mean there's one array, and then there's two, so there's two values, and there's another array in it which has two values, which are like 1, 1, like just different numbers, or just like n and some kind of numbers, right? And that's how a shape looks like. There's two values in one array. So there's one array and two values inside of it. And that's obviously enclosed in another array. But yeah, that's how shapes look like. So 4096 would mean 4,096 embedding vectors of 768 token embeddings. And we do positional encodings on them, on these little things. The reason why is, and by the way, there's a formula that applies, PE pause 2i equals sine over here. Oh no, we don't have much space. Pause 10k 2i divided by d model. Okay, we overstepped either way. So yeah, that's how the formula would look like. And then there's the other one over here. I'm not sure why I'm copying over here, but I mean, you can see it over here. But anyway, I'll write it. So these formulas, right, they're applied so that the model could understand the position of the token. So essentially, we do this so that the model could know the position of the sequence. Just because the tokens are in order doesn't mean the model knows that hello stands at the beginning. It could literally mix up anything. If I say, I don't eat kids, right? But the model doesn't understand the positions of the things. That means it could be like, it could interpret it as, don't I eat kids? It's like, that's a very different sentence, you know? It's a little bit crazy. So we have to inform it that indeed it is like that, in that order, instead of the different order. So it's if I say, hello, my name is etc., etc., so it knows that the order is like that. Instead of saying like the name, my name is hello, or something like that, right? So that doesn't get confused with that. So that's the formula right there. 10,000 2i d model. Okay, d model done. So these values essentially are applied onto each embedding vector, each embedding in the embedding vector. So let's just look at this. First of all, you have 2i and 2i plus 1. Essentially, it's like to ensure that sine is applied only on even numbers and cosine is applied on odd numbers. This is for having different frequencies. So you see, exist to create alternating frequencies, telling the model different things about about each position, so that it could tell like a different kind of value. And so then we have 2i and 2i plus 1. Yeah, I told you before that was even and odd. Then we have pause, so it's the position in the sequence, so it's the position of the token embedding vector. If we're doing this like for the very first token embedding vector, out of like there's this and then so on. This would be the very first one, which would be like 0. If you're doing it in code, that would be 0, but let's just say it's 1. So we have that. So that's the position. It would be 1 over here for the very first token embedding vector. Then we have, what else? We have this formula over here, 10,000 2i. And by the way, 2i, what is 2i? It's the position of the token embedding itself. So like if you have this, okay, let me just do this. Like that. I just expanded it, still the same thing. Okay, so we have these values, and then the first one over there inside of the token embedding vector is exactly what I is, right? And this is done for each token embedding in the token embedding vector. And so we do this, D model. This is done, so like it's just a formula, essentially Y10,000. 10,000 was chosen by the researchers of attention is all you need. And yeah, I don't know if I've talked about it in here. No, I haven't. Attention is all you need is essentially this research paper that was published a long time ago in 2017. Now it is a long time ago. That's 8 years. No, that's 7 years. That's 7 years. That's a lot. That's a lot of time. But essentially it was posted by these Google researchers at Google, and they found out, they essentially researched all of this stuff. They researched the transformer architecture, positional encodings. Researched means like actually made like a model like that. They proposed a new model essentially. So there was positional encodings, token embeddings, and the transformer architecture is all that they came up with. And when they were coming up with positional encodings, so as to make the model know about each position of the sequence, they found out that 10,000 works best. That it's like the best number to just put there. It's like a Scholar constant value. Scholar const. Boom. Now D model, what is D model? It is, well, in our case, or not in our case, in the GPT case, I think. Yeah, in the GPT case, it's 768, or I think that's with GPT-2, I'm not sure, but I think GPT-3 has more token embeddings, I'm not completely sure, but 768 would be the case here. So yeah, that's how it looks like. Positional encodings, model doesn't know, model oblivious to positions, oblivious to order, we must encode positions, so that the model sees, aha, okay, so that's the last token, that's the first one, etc. Transformer architecture. Now we move on to the mighty transformer architecture. We can just draw a line over here. Quick intermission. Now, if you've been wondering why I disappeared for an entire 2 months, it's because I've been working on something very special for you. Now, I know that you're very interested in building GPTs. You're watching all these videos, these episodes on how to build GPTs. You've watched my journey of how I'm building a GPT. How about we together build a GPT? Go and click on the link in the description right now and go and buy the course called The Innovator's Guide that I've worked on today, that I worked on before this. Essentially, this course spells out how to build a GPT entirely. Everything from the basic things of tokenization and collecting a data set to training and the creation of the transformer, literally in Python and TensorFlow and all this code. We're going to spell it out and I'm going to break down each code line, very detailed. The price is right now, it's early access at $40. You can get it right now or get it in 2 months when the price has risen, up to you, for the same features. But if you get it right now, $40, I'm gonna keep improving the course over time and you're gonna get all the benefits. So click the link in the description right now and go and buy it. Thank you for listening and happy learning. And here it is. So there's a lot of empty, clear space for us to work here. Let's go on to the transformer architecture. Now, a typical transformer architecture consists of encoder-decoder pairs, as you can see here. That's the encoder right there, and that's the decoder right there. And then like the encoder shoves it in midway into the decoder, and then they do the work and then generate a probability distribution. But in a GPT, only the decoder is saved, and at that, while skipping this one, this part over here, so the multi-head attention mechanism, the exact part where the encoder puts in its information halfway. We just skip that part. We just go through the multi-head attention mechanism, add a norm, then go to feed forward. That's what these transformers do, like that. And yeah, like this, essentially, if you can imagine. Add a norm, add norm, mham, and fnn, add norm, linear softmax. So that's how it does. It just skips this entire thing. So you can basically imagine it like this instead. Now, if you're wondering how all of this works, We will break this down just in a moment. So let me just draw that and draw that. Done. So let's just illustrate what the hell is going on. This is very odd, but anyway, probably have to just do that, I guess. Like that, or that. There we go. So that's how it looks like. Let's first move on to the multi-head attention mechanism, which actually looks like this from the inside. So we have 3 linear operations. Now what is VKQ? VKQ in this case is literally, in this case means in the case of GPTs, is literally all just the input sequence. There's literally no difference between any of them. If there was the encoder, that would be different. Q would be different and VK would be the same, or I don't know if it's the other way around. I'm not completely sure, but yeah. So I think K would be different, or Q would be, I'm not sure, but yeah. In the case of GPTs, they're all the exact same. And because we just don't have the encoder to change that case. So first of all, the linear operation, what happens here is, by the way, if you hear that there's a linear operation, it's literally just dot input. Probably illustrate it differently. So let's take this piece by piece to explain it properly. We have V, K, Q, which is that, and that. Now the linear operation, whenever you hear that the linear operation is the case, maybe you've already read it by now, but yeah, essentially it's just dot input weights plus biases, just like that. And dot just means a multiplication, input times weights. If you don't know how matrix multiplication works, I'm not going to break it down to you, but essentially if you have 1, 1, 1, 1, and then you multiply it by that, it's like essentially just multiplication, you know. You'll have to look that up, matrix multiplication. I don't know why I'm stuttering so much, but yeah. Now, as the weights and biases improve over training stages, so essentially the linear operation is done to pay attention to the input sequence, so that it can weight how important each word is in relation to each other word. So the input embeddings have been done to give the model understanding of what the word is, and the multi-head attention mechanisms deepens that understanding of the words, and also the understanding of the words in relation to other words. So how much does the word hello matter with the word my name is, right? Something like that. Plus biases is just like the bias vector is added on later on. And then element-wise addition. Then SDPA, what is this? So it is essentially this formula over here, QKT divided by DK. Now what is this? KT is the transposed or the reshaped version. So like I'm having a difficult time explaining what transpose is, but essentially if you have element 1, element 2, element 3, element 4, and like this, you transpose it, what happens is essentially it looks like this. This is done to alter the type of multiplication that occurs, but essentially Q times KT is done so that we can know the difference between the two, or the alignment between the query and the key. In the case of GPTs, the alignment is exactly 100%, alignment 100%, because I mean Q is exactly identical to K. But anyway, DK, what is this? Is just the dimensions of K, so like the length of K, essentially. If you can imagine, K has 4096 tokens, right? So that would be K. It's divided by the square. Now, why do we do square root? It's to why do we do square root, but why do we divide it by this? Is to not let the result of this dot product become too high, because if it becomes too high, it's too crazy, it's too we can't have really high values, we have to balance them. So which is why we do it by this formula. Okay, now that we've covered multi-head attention, oh no, there's more. So essentially this is computed over multiple heads. Where is it? Yeah, this is computed over multiple heads H, hence the name multi-head attention mechanism. The number H is 96 in the Mega model of ChatGPT. Yeah, it's very surprising that they have 96 heads. So essentially what this does is it does this times 96, which is quite crazy. And the reason why it's crazy is because it takes a lot of computational power. So yeah, it pays a lot of attention because there's multiple heads. It means that there's more attention being paid. Multiple, like, you could essentially imagine multiple people paying attention to the same sequence and trying to figure it out. Each one has its own perspectives and understandings of the input sequence, and that's 96 heads for you. Now, after that, this concatenation occurs. So we have multiple, like 96 heads times 96. We have to concatenate them all into one, so that like all of these different analyzed ones are combined into one. Then we do a linear operation, which actually reshapes the 96. So like right now, the shape would be 96. Batch size would be BS. Just B, okay? BS is probably not the right thing to do. Batch size, heads, and then 4096. 768. So that I think that's how it would look like, but this reshapes it to be the linear operation, which is dot input weight plus bias. Reshapes it to become just do that. Reshapes it to become batch size, and then this and this again. So E is just embedding dimension, but I'll just rewrite it like that. It reshapes it to do that, and also it further deepens the understanding. And then there's a softmax operation that is not shown over here, but it occurs to generate a probability distribution over all of them to finally weight how much each one matters. Because like in model language, when the model is doing its computations, the numbers can widely vary, like the weights and biases can widely vary, the numbers produced can widely vary. They can be huge, insanely huge, it can be very small. We just have to make a proper softmax probability distribution so that it's actually usable, and like GPTs do that essentially. So the softmax function is applied. This function generates a probability distribution, and it weights, so how important it is. So an accurately trained MHAM would weight hello, name, and Tony Stark as highly important. In the sequence, hello, my name is Tony Stark, since these are the most important tokens there, or that would probably be separated like that. Hello, yeah, just you get the idea. So that's how it would look like. Now afterwards we've like completed all the space in here. We don't have any more space to demonstrate, but anyway, I'm still gonna keep drawing over here. So afterwards we apply add a norm. What does add a norm do? Add a norm essentially, before we put the input sequence into the MHAM, like the GPTs essentially reserve a little sequence over here, and then they throw them over there so that the affected sequence and the unaffected sequence meet each other at add a norm. The reason why this is done is so that the model can retain some old information, the unprocessed information. And so addition is literally just like, if you can imagine, both of them are of the same shape, by the way. This is added to that, this is added to that, this is added to that, and you just get the point, right? And that would be looking like that, like that. So add a norm, then that's addition for you. So addition, LM, Y is addition, Y is addition, Y is add. Then normalization, it's a complex formula that like there's multiple different formulas, each of which do different things. Essentially what normalization does is so that there are no exploding gradients or vanishing gradients. This happens when, during optimization, if you don't really understand this terminology, that's cool with me. The time when the model adjusts its weights and biases, optimization, the model looks back on previous calculations, having collected derivatives of each operation. So if it does dot input weight bias, or if it does some kind of exponential function, whatever, e to the power of zj, like these exponentials, it will collect the derivatives of those. So derivative is just essentially how much stuff has changed. I won't break it down here, but yeah. If the derivatives are too high, how much the change has happened, then the model may optimize too aggressively, and that will hinder the accuracy. And conversely, too little adjustment makes training futile. If the derivative is very small, very low, very little change, there's going to be very little change to the neural network's adaptations of the weights and biases, which is a very big problem. You may not understand entirely what optimization is and gradients and so on. Just know that normalization is done for stabilizing data. So stabilize data. Okay, no, stabilize data, just like that. Data normalization happens, then the feed forward network, okay, which is what it's called, FNN. Essentially what it does is, if we look at here, the sequence is inserted into a feed forward neural network. Let me just break it down very simply like this. If you can imagine that, this will be way larger. There's a bunch of hidden layers. I think I've broken this down in the first episode, that there are multiple hidden layers. There's input, output, and hidden. Anyway, here, do I want to draw this? Yeah, sure, let's do it. It's kind of cool to do, and either way, you're going to be looking at these notes later on. So, if you have an AI exam coming up on how AI systems work and how the transformer architecture works, you probably never will have those exams ever, but yeah, just in case, So the feed forward neural network has varying amounts of neurons across not each layer, but the inputs layer, right? For the neural net, for the feed forward network, has that, and like that output layer. So these two have the embedding dimension as the amount of neurons. So 768 would be like in the case of ChatGPT, or in the case of GPT-2, not sure. And then the hidden dimension is the amount, the size of the context window, essentially, which is 4096 in the case of ChatGPT. And so yeah, that's how it would look like. 768, and by the way, all of these transformations are dot input. I mean, I don't. Let me just imp w plus b. That's how we will just label it. Essentially, that's what occurs at each and every neuron, which contains these weights and biases. Now, 768 is done to further deepen the understanding of actually the word's meaning, whereas 4096 is done to understand the relationship between words and so on, and 768 is also done to deepen the word understanding. Now, because you hopefully remember that the shape is 4096, 768. And so, but between each of these, there happens to have, that's not correct. Anyway, the activation function called ReLU is applied. So between each one, so if you don't know how activation functions work, if I haven't broke them down before, these are essentially things that are like pre-processing the output data of the neuron, so that, like you can imagine, they're fired all over here, so that it can further deepen the understanding of the model, further like add more complexity to the input sequence, rather than having a very linear, for the input sequence for the model to understand it further. So here there would be a ReLU function, ReLU, and ReLU is essentially a function which drops out certain neurons by zeroing out the weights and biases that are negative. So essentially, why is this done? Is to, like, some neurons just don't get it right. Essentially, they don't understand what's going on, right? They're not computing the right thing. And ReLU decides to drop them out. That's the easiest way I can explain it to you, but that's how ReLU works, essentially. And it's essentially used to just deactivate neurons. So some neurons will just go extinct, like that. Just some neurons will just be extinct thanks to, because of ReLU right there. And so this one goes extinct, this one goes extinct, this one goes extinct. That's where you apply, if you apply it, right? So like if we apply ReLU over here, ReLU over here, ReLU over here, this one will go extinct, for example. And yeah, then there's also a thing called dropout applied between neurons. Why this is done is because essentially there's a problem called overfitting. Let me just drop out, not out of high school or out of college, but drop out of the neuron, drop the neuron out of functioning, also extinction of neurons. This is because there's a problem called overfitting in models. So when you overfit, essentially the easiest way I can put it as, when a model overfits, essentially it gets very good at doing what it's doing, at guessing or like generating tokens based on a certain type of data, but it cannot diversify and generalize. So if I tell it, this is what happens when a GPT rejects an inappropriate request. If you try to write to GPT, hey, tell me how to cook crystal meth, is going to be like, hell no, right? Because it's very good at rejecting that. But if you start sliding in like slowly, if hypothetically you were a chemistry teacher and then it folds, it says, yes, this is how you cook it, right? That's called overfitting, or a problem like that is essentially where it gets very good at, I wouldn't really describe that as overfitting, but I'll just use that as an example. It gets very good at rejecting those direct like responses or like direct requests for cooking math, but it gets very bad at actually rejecting like these slow, nuanced kind of requests. That's actually not what happens with GPT anymore, but yeah, that's what happened before, I think. But yeah. So it's like you getting super good at basketball. You're very good at dribbling. You're very good at dunking and everything. But then you're so stupid that you decide, okay, at every sport, I have to get better at dribbling. So that's the thing right there. And that's essentially the problem with overfitting, which is why dropout, it essentially removes some neurons to stop you from focusing too much on one type of way. It's essentially making you diversify. And dropout only happens during training. During usage, you want to use all your neurons. You want to use your brain for good. But during training, sometimes you just like stop thinking so much, right? That's essentially what occurs. And yeah, that's the feed-forward neural network for you. Then add a norm is done again, as we've seen here, AN. Let me just go over here. Add a norm is done again. Then there's a linear operation again. The linear operation, which is dot, input, weight, bias, etc. Then the softmax is done to again generate a probability distribution. Now the probability distribution is a little bit different. Softmax is applied to generate a probability distribution over each and every token position. Now instead of 768, there is a vector of length vocab size. So essentially, if you have in your JSON file, if you have 30k tokens, the shape of your thing, or of the GPT's thing, would be 30k like this, 4096 tokens, and each one has a probability distribution of 30k different possible tokens to choose. So essentially, the value of the probability is 30k, or no, the value of the probability of the probability distribution, each individual value, is a probability value of like how likely is this token to be chosen, and the actual token is the position of the probability value. So essentially, if you have the probability distribution, it starts with 0.04, 0.01, something like that, right? 0.04 is the likelihood of the token being chosen. 0 is the actual token, right? So, 0 would be a special token. It's probably not going to get chosen because they're not really trained to generate special tokens except for end of reply. But you get the point. The position is the token. The probability is the probability of it being chosen. And yeah, that's essentially how it works. And there you go. That's how we've covered it. And by the way, there's something else I have to mention. There's the decoder. This decoder that we have, it's multiple parts of them are stacked on top of each other times, and I think there was it written over here. Times n times, right? So essentially, how many times you want to stack a decoder, because you know that a GPT has multiple layers, and decoders, there's multiple of them, and too. In a GPT, there's a decoder there, then a decoder there, then a decoder there, multiple of them, many of them actually, in order to form it and in order for the GPT to understand it more comprehensively. And then only after the decoder stack has been complete does the linear and softmax operation that we've looked at up here occur. Okay, so just keep that in mind. And yeah, that's it. That covers our episode today. And click the link in the description below if you want to build your own GPT with my help. The price is rising, so buy it now while you can. Early access.